The number e. Where did it come from? What's it for? What does it do? Is it equal to pi? These are all important questions, and so I'm going to start off by introducing vaguely what it is as a number. So if we think about the number pi, we know that if we have a semicircle of radius 1, then this arc length around here is pi. And so in that sense, pi is the circle constant. E is a bit different. E isn't so much a geometric thing, although you can relate it to hyperbolas. E is a number which is to do with growth and rates of change. And so the first time it was discovered was by Jacob Bernoulli. Even though we call it Euler's number, Euler wasn't the first to find it, Jacob Bernoulli was, and he was interested in this hypothetical problem of, let's say we have a bank and it's a really good bank, and this bank, we put in £1 and after 1 year it gives us 100% interest. Okay, and so after 1 year the amount that you have, it's pretty trivial, it's just £2, right? Which is pretty amazing. But it would be even better if we could have, say, 50% interest twice a year. So then we put in our £1, add on 50% to that, and we get £1.50. And then if we add another 50% to that, we get £2.25. So that's a little bit better. If we did this 10 times with 10% interest instead, we'd get our £1 going to, I think it's £2.59, I hope that's right. And the way that you can calculate this on a calculator very easily is, well, we have our £1 and we're multiplying by 1.1, and that gives us our extra 10% every time we multiply by 1.1, and we're doing this 10 times. If instead we had, say, 1% interest 100 times a year, that would get us our £1 multiplied by 1.01 for the 1% interest, and then we do this 100 times. This gets us £2.70. And so you might think that if you keep splitting up your interest into smaller and smaller chunks, you can get as much money as you want. You get infinite money. But this isn't actually the case. So what we're looking at here, all these numbers are of the form 1 plus 1 over n to the power n. And so that's increasing our value of £1 by an nth n times. And it turns out as n approaches infinity, the value of this expression does not approach infinity. It actually approaches a very special number, which is called e, which has a rough value of 2.7183, something like that. And so what I'm going to do today is show you that this expression, as you take n to infinity, does converge to some finite value, and you can't get infinite money from this process. So, how can we get a better grasp on what this limit is? Well, one thing we could try is expanding out this expression 1 plus 1 over n to the power of n binomially. And that will give us, the first term will be n choose 0, the next term will be n choose 1 times 1 over n. Next term after that will be n choose 2 times 1 over n squared. And we'll have lots of terms. Our general term will be n choose r times 1 over n to the r, and our last term will be n choose n 1 over n to the n. Running out of space there, but that's fine. And so this might look like it hasn't helped very much, but there's a very interesting thing which happens as you take n to approach infinity if you look at each term individually. So let's just, for the moment, have a look at this bod, and in order to be able to talk about these terms, I'm going to name them. This general term will be TNR, so this will be TN0, TN1, TN2, TNR, and TNN. So what we'll need to do to evaluate TNR as n approaches infinity is we'll need to get this n choose r term, And we can look at the factorial definition of n choose r, which is n factorial on r factorial n minus r factorial. And this n factorial over n minus r factorial, a load of these linear terms will cancel, and we'll get n minus 1, n minus 2, and so on, up to a final term of n minus r plus 1, and then divided by r factorial. And now we can introduce this to get a better grasp on TNR. So TNR is just n choose r divided by n to the r, and so TNR is going to be equal to n minus 1, n minus 2, and so on, up to n minus r plus 1, divided by r factorial n to the r. But we can actually rewrite this n to the r as being n times n times n times n, and so on, not n times, r times n times n times n, and to our last n, r times. And so there are r n's on the bottom, and on the top there actually are linear factors. N to n minus r plus 1 is r terms, and so we can actually pair these up. So we can pair an n up with an n, the n minus 1 with an n, the n minus 2 with an n, and all the way up to our final term of n minus r plus 1 divided by n. Okay, and when we do this, we can write this in a way which will make the limit as n approaches infinity very clear. So this is 1 over r factorial times n over n is just 1, times n minus 1 over n, that's just 1 minus 1 over n. N minus 2 over n is just 1 minus 2 over n, and so on, up to our last term of n minus r plus 1 divided by n, which is just 1 minus r plus 1 over n. And now, as n approaches infinity, these fractions here will approach 0. And so this TNR, which is the product of all these, will approach just 1 over r factorial. So we have limit as n approaches infinity of T n r is equal to 1 divided by r factorial. And now we can have a look at simplifying this 1 plus 1 over n to the n. I had to open a window because it was getting hot in here with all the spicy maths. So if we have our 1 plus 1 over n to the power of n being this sum here, and we know that as n approaches infinity, TNR will approach 1 over r factorial, then we can take the limit as n approaches infinity of 1 plus 1 over n to the power of n. And we know that Tn0 will approach 1 over 0 factorial, Tn1 will approach 1 over 1 factorial, Tn2 will approach 1 over 2 factorial, and so on. And we'll have a general term of plus 1 over r factorial. And this is an infinite sum, and I'm running out of space. Right, now, this is the value of e written as the reciprocals of the factorials, all added up. I'm going to group together this 1 over 0 factorial and this 1 over 1 factorial to get 2. And then I'm going to write 1 over 2 factorial as just 1 over 2. I'm going to write 1 over 3 factorial as 1 over 3 times 2. And we're going to have our 1 over 4 factorial. And so on. And the reason I've written this expression out as this is because we still haven't showed that this evaluates to something which is finite. But we're going to do that now, because if we consider a different infinite sum, 2 plus a half plus 1 over 2 times 2 plus 1 over 2 times 2 times 2, and so on, then a half is equal to a half and 2 is equal to 2. That much is clear, right? 1 over 2 times 2 is greater than 1 over 3 times 2. And 1 over 2 times 2 times 2 is greater than 1 over 4 times 3 times 2. And each term in this infinite sum would be greater than the respective term in this infinite sum. And so this whole bod here is greater than this sum, and so E is less than whatever this is. But this is actually not too hard to compute, because a half plus a quarter plus an eighth and so on, this is just a geometric series and it evaluates to 1. And so E is less than 2 plus 3. Oh, 2 plus 1. Which is equal to 3. Getting ahead of myself there. Right, and obviously E is also greater than 2. And so yeah, this is the finite value which our compound interest will take us to if we choose smaller and smaller divisions. Hope you enjoyed the video. Next video, hopefully coming out quite soon, will be showing why the function e to the x differentiates to itself, and that will be using this definition of e which we worked with today. So that'll be coming out soon. Until then, adios. This isn't out of shot, is it? Hang on.